Hello everybody, Mr. Hinnon here for a little Henstitute Help. So this little guy over here is supposed to be me anyway, so he's just lounging, enjoying some nice little fun over there. But since I can't be here, I figured, or just if you need some extra help on these, I thought I would start us off with a Henstitute Help on the concept questions and then kind of go from there. So we'll see how things kind of go. So to start off with, we're dealing with density and Archimedes Principle. So the key thing here is density is described as mass divided by volume. Okay, so that is a key idea. However, both of these concept questions kind of deal with density, but they also deal a little bit with Archimedes Principle. So Archimedes Principle kind of stems from the idea that when you place an object in some fluid, doesn't have to be water, just any kind of fluid, it will displace its volume of water. However, if you find the mass of that displaced fluid, that'll be equal to the buoyant force. So when figuring all that lovely stuff out, basically we end up with two equations. So I'm going to try to type them up here just real quick, and then we'll end up using them later. The first thing I got to do is I got to insert a special character. So the character we're actually using is the Greek letter rho to represent density. So that's kind of looks like this. When you type it, it looks like this, Greek letter rho. So I'm going to put that in there, and that equals, whoops, get that rid of there. That equals, nope, don't change that. I hate when it likes to change things. That's going to equal your mass divided by volume. So that's the equation for density. So this is not a P, that's density. The other one is the fact that the buoyant force, so F, and I usually do a little subscript. I'll just do it this way, subscript B to indicate buoyant force is equal to the weight of displaced fluid. So we know the weight normally is mass times gravity. However, if you're trying to find the mass of something, we can actually borrow that density equation and realize that it's also equal to density times volume. So the way I like to write this is, let's see if I can get my equation to actually go in there. So it'd be density, volume, and then gravity. So we'll see this equation pop up a lot. But we're also, in some of these problems later, we're going to need to use Newton's laws, the idea of drawing free body diagrams. So when you get into the problems, we'll see that. Okay, let's start with question number 1. So we got a beaker, it's full of water. A solid object of mass 3 kilograms is lowered into it. It's fully submerged in the water. During this process, 2 kilograms of water flows over the rim and out of the beaker. What is the buoyant force that acts on the submerged object? And when released, does the object rise, sink, or remain in place? Okay. Buoyant force is going to be this, the weight of your displaced fluid. So it would be the 2 kilograms of water that flows out multiplied by gravity. So 2 times 9.8 is 19.6. Okay? So we have 19.6, 19.6, 19.6, D, E, and F. It's not A, B, or C. What is 29.4 newtons? 29.4 newtons is the weight of the actual rock. Okay, so, or the object, it doesn't say it's a rock, kind of looks like a rock. But 3 times 9.8 is 29.4. So that's why A, B, and C have 29.4. That is not the buoyant force, that's the weight of the actual object. It's going to be important in just a moment. So the buoyant force is either D, E, or F. The next step. If the object weighs 3 kilograms, but it only displaces 2 kilograms of water, that means the force downward on it is 29.4 newtons, and the buoyant force, the upward force, is 19.6 newtons. Okay? So if I apply more force down than I apply up, that object is going to accelerate down. So if you were to cut the string on this, this object would sink. So we are looking at an E here as our correct answer, and you would all highlight E. Okay? Pretty straightforward. Next up, number 2. 3 solid objects are floating in a liquid as they have different weights and volumes but have the same thickness. So in other words, the dimension you can't see into the page is the same. Rank the objects according to their density, largest first. Okay, so when we have an object floating in water, one of the things we're going to know in all 3 of these cases is that the buoyant force is going to equal the weight of the object. Okay? And since the float is going to be more buoyant force is going to happen when you are deeper in the fluid, that's going to have a relationship with your density. So if we kind of come up here, volume for these objects is basically going to be length times width times height. So height I'm going to say is the depth in the water, so it's the vertical distance. I don't really care about the length and the width. Those are not important. The only one that's really going to be important here. So if we have the buoyant force equaling the weight of the object itself, then when you have a larger h, then what that means is that you must actually have basically when it's deeper in the water, you have to have a larger density because now the fluid is trying to kind of do that. So what we're dealing with is kind of, I'll kind of describe it this way. You could have a rho Vg equal to another rho Vg. The rho Vg for the water that is floating in, or the liquid in this case, should be equal to the rho Vg for the object. You can actually use rho Vg for objects as well. That's what's great about it. So the rho Vg for that object as well. And so if those are equal to each other, if the depth on one is larger, then the density on the other has to be larger so that we actually have them balanced. So the deeper it is, the more dense it is. So if we're looking for the largest first, that would be C. Next up is A, and it's only the depth. I don't care about the width of it, it's only the depth that's in there. And then B is actually the least dense. So we're looking for CAB. CAB looks like another E down here. Highlight that, but bam. I hope that helps.